In this video, we're going to look at using Avogadro's number. So what is Avogadro's number, or the Avogadro constant? It is the number of elementary particles in 1 mole of any substance. So it's this fixed number of particles that basically defines for us what a mole is. And it's usually given to 3 significant figures as 6.02 times 10 to the power of 23. And the unit is essentially per mole. We'll think about that unit in a moment when we look at some of the calculations. So it's not used very frequently in A-level questions because most of the time, for convenience, we count particles in moles, not in individual numbers of particles. But you do need to recognise when to use it, which we'll look at more in this video. As we've mentioned before, we're using this term elementary particles, and that's because we can count literally anything we like in moles, and therefore the constant will refer to numbers of any type of chemical entity. What do we mean by that? Well, if we have 1 mole of neon, neon is a noble gas and exists as single atoms, and therefore 1 mole of neon contains 6.02 times 10 to the 23 neon atoms. If I was looking at something like CO2, 1 mole of CO2 contains 6.02 times 10 to the 23 CO2 molecules. And if I was to look at an ionic substance, and this is where it gets interesting with some of our calculations, 1 mole of sodium chloride, that will contain 1 mole of sodium ions, and therefore it will contain 6.02 times 10 to the 23 individual sodium ions, and then it will contain the same number again of individual chloride ions, because 1 mole of sodium chloride contains 1 mole of sodium ions and 1 mole of chloride ions. So let's look at some examples of where we might use the Avogadro constant in calculations. The units of the Avogadro constant are given as mole to the power minus 1, which is just basically because it is the number of something per mole. One way in which we might therefore be asked to use the Avogadro constant is to calculate the absolute number of particles in a given amount of substance. So here's our first example. Calculate the number of molecules, so it does not say number of moles, it says number of molecules, in 3.6 grams of H2O. So my first step with this, because the Avogadro constant is in per mole, is to work out the number of moles, which is my first step for pretty much every chemistry calculation I do. So I've got the mass is 3.6 grams, and the molar mass of water is 18, and that gives me a number of moles of 0.2. In all of these calculations, just to save me writing out the Avogadro constant over and over, I'm going to use the shorthand, which is a sort of like capital italicized L. So I'm going to take 0.2 times Avogadro's constant, and that is going to give me 1.204 times 10 to the 23. And I don't stick any units on this because number of molecules doesn't have a unit, unlike the mole, which is a unit. This is just an absolute number of molecules. So it's always going to be quite a large number when we're doing that type of calculation. Another example of this, slightly different. So the number of hydroxide ions in 1.924 grams of magnesium hydroxide. My first step is going to be exactly the same. I'm going to work out moles, and just to be super clear, what I'm working out initially is the moles of magnesium hydroxide. So I'm going to do 1.924 divided by the mass of 1 mole of magnesium hydroxide, which is 58.3, that's my MR, and that gives me 0.033 moles. Now that's the moles of the whole substance, but when I look at the formula of magnesium hydroxide, I can see that for every 1 mole of MgOH2, there are actually 2 moles of hydroxide ion present there. A way to imagine this is if you thought about it going into water and dissolving, you know that ionic substances, they split up into ions in water, and you would make 1 mole of magnesium ions, but for example, if you were writing an ionic equation, you would make 2 moles of hydroxide ions from that if you were to split that compound up. So that means that to calculate the number of hydroxide ions, I need the number of moles of hydroxide ions, and so I'm going to times it by 2. That gets me moles of OH minus, which is 0.066. Then I do exactly what I did before. I've got moles, I want the number, so I multiply by Avogadro's number. 0.066 times 6.02 times 10 to the 23, and that gives me 3.97 times 10 to the 22. Again, no units, it's just the number of hydroxide ions. And there are a few other ways to use the Avogadro constant. So in the previous 2 ones, we've calculated the absolute number of particles, whether that be ions or molecules. But we can also use it to convert from things that are measured per mole to absolute quantities. So here's a couple of really common examples of this. This one's used in mass spectrometry sometimes if you have to do time of flight calculations on your course. So it's asking for the mass in kilograms of a single ion of 85 isotope rubidium. So the fact that it's an ion isn't going to change its mass because that losing or gaining electron doesn't have a significant effect on the mass. So we can assume that we're using this number 85, which is the mass number or the relative isotopic mass. What does that mean? Well, it means the mass of 1 mole. So what that means is that 1 mole of 85 rubidium weighs 85 grams, because remember our relative atomic masses are expressed in grams per mole. So we also know that the Avogadro's constant that we've got up here is the number in a mole. So it's how many there are. In this case, how many rubidium-85 ions there would be in this 85 grams. It therefore stands to reason that the mass of an individual ion is in grams is going to be 85 over Avogadro's number, because that's how many there are. And that's going to give me 1.41 times 10 to the minus 22, but we need to be careful because that answer is in grams, because our relative atomic mass is expressed as the mass of 1 mole in grams. And so to get it into kilograms, I just need to divide by 1,000, and that gives me 1.41 times 10 to the minus 25. Another example of scaling from a molar quantity to an individual quantity. So mean bond enthalpies are measured in kilojoules per mole. So what that tells me is that for every mole of carbon-fluorine bonds that are broken, we need to put in 467 kilojoules. And then the question is asking for how many joules are needed to break a single CF bond. Now there's more than one way you can do this. Previously I converted to kilograms at the end because I had my answer in grams. So this time I'm actually going to convert to joules straight away as my first thing to do. It's an easy thing to do. So 467 kilojoules is the energy to break a mole of bonds, times it by 1,000 gives me 467,000 joules, and that is the energy needed to break 1 mole of bonds, and hence why it's measured in kilojoules per mole. From there, well, if that's how much energy is needed to break a whole mole of bonds, this number, Avogadro's number, is the number of things in a mole, and so I want to know how much is needed to break one bond. So I do the number for a mole divided by how many there are in a mole. I'm just going to write L again for shorthand, and it's going to give me 7.76 times 10 to the minus 19 joules. A small number. I'm expecting it to be a small number. It's one bond, like it's not going to be a lot of energy. One bond is not a lot to break. So when do you use Avogadro's constant? The problem is that when we teach it, we don't use it very often, and people sometimes actually tend to try and use it when they don't need to. In the past, you used to be given a big clue. So if you look at old papers, they will often include Avogadro's number in the question. But you're not going to get that anymore. So the value is now generally included in a data booklet or a formula sheet that you're just expected to have with you, with the periodic table and some other numbers on there. So you won't get a clue in the question in terms of the number being right there for you to use, although that might still happen in tests. So what clues can you look for? Well, what you can do is look for the wording in the question. So having a look at A says calculate the number of moles of hydrogen atoms in 18 grams of water. Do I need to use Avogadro's constant for this? No, I don't. And the reason I don't is because it's asking me only for number of moles. So for number of moles, I do mass over molar mass. No need to involve Avogadro's. It is moles of hydrogen atoms, so I would need to then consider the formula like we did for magnesium hydroxide and the ions, but I don't need to calculate actual numbers. Number of hydrogen atoms in 18 grams of water, then yes, I will need to use Avogadro's because it doesn't say number of moles, it says number of atoms. And then in C, the number of nitrate ions, again, I would need to use Avogadro's for that because it's not saying the number of moles of nitrate ions, it's saying the number of nitrate ions. So a lot of the time, if you're just doing your normal calculations between moles, mass, volume, concentration, there is no need to use Avogadro's constant. It's only if it asks you for a specific number of particles, such as the number of ions or the number of atoms, and it will usually be a fairly standalone question. There is one case where we don't do that though, and that's when we're just considering relative amounts of substances. So this is really common, particularly with a multiple choice question. It says which of these amounts of substances contains the greatest number of chloride ions, and then we have our masses and our formulae of our substances. So because it says number of chloride ions, you may be tempted to go all the way to working out the actual number of chloride ions. So to do that, for example, with A, I would do my mass, 3.30. I would divide it by 133.5, which is the relative atomic mass of aluminium chloride, and that gives me 0.0247 moles. And then that's moles of AlCl3, so I can times it by 3 to get me my moles of chloride ions, which would be 0.0742. So I could do that for all of that. Now, what you might be thinking is, well, that's my moles of chloride ions, and you've just said that if I want to know the number of chloride ions, then I would times it by Avogadro's number, and that's absolutely correct if the question was actually asking me to do that. But moles are proportional to the actual number of ions. So if you think about it, if I do this method for every single one, 10 over the MR of CaCl2, and then I would times it by 2 because there are 2 moles of chloride ions per mole of calcium chloride, I would be timesing every single one by Avogadro's number at the end. There's no need to do that. So you can just compare the numbers of moles, and that is proportional to the number of chloride ions. So if you just need to put things in order or decide which is the biggest or which is the smallest, you do not need to work out the absolute numbers involved. So if you want some more help with your A-level chemistry calculations, I've got a full online course, which actually this video was modified from. It's called Confidence in Chemistry Calculations. And at the moment, you can get that absolutely free for 2 weeks. Let me just show you what's in the course. So there are 8 different modules which look at the essentials, equation skills, relative atomic mass, formula mass, empirical molecular mass, percentage yield, atom economy, all these different things, titrations, loads of stuff on solutions, calculations, also Avogadro, and long answer problems. So there are some like really more challenging ones, and it comes with a full booklet of different chemistry calculations with full mark schemes and explanations as well. All of the more difficult questions that I put on there have video walkthroughs. So you don't just get a mark scheme, you actually get how to do it. Each one of these modules has like at least 6 different lessons in it, quizzes and ways to assess yourself. And actually you can access this course as part of my A-level revision memberships, which includes loads of other different topic videos and practice questions, and not just the calculations course. So the calculations course is included in the bronze, silver and gold membership. The only difference between the 3 of these is that with the silver membership, you get a full monthly assessment where you do an assessment exercise and I mark it for you, give you that examiner's perspective, give you personalized recorded feedback. And with the gold membership, there's just a few spaces left for my AQA and OCRA group chemistry lessons. Those are for year 13 because my year 12 course is full. But if you just wanted to try out the bronze membership, which is only £5 a month anyway, including the whole calculations course and 22 other different topics, along with practice questions and masterclass videos, that's actually available right now for a 2-week free trial. So you can try it, see how you get on, and if you can't even afford the £5 a month, you could sign up if you've got like a mock exam or a retake coming up. So go to my website, ckchemistry.co.uk. You'll also find loads of free revision downloads there as well. And of course, subscribe to my YouTube channel because I'm going to do at least 1 video a week and probably 2 for the next term or so.